Today we're going to talk about two things. One is electroplating and the other is electropolishing. And I'm going to start off with the whole idea of electroplating. In fact, you've already been introduced to this already because I mentioned it several times, and I in particular mentioned it last week when we were talking about tin plating, which is actually an example of electroplating. So in the first slide, just to give you an idea of what we're talking about, we're primarily talking about industrial electroplating. And the basic idea is that we're protecting our metal, which might well be steel, or it might well be stainless steel even, or it could be another metal, it could be copper, it could be almost any metal. But generally speaking, it's a metal which might otherwise have a corrosion problem if you did not do something about it. And electroplating is used to put a thin layer of another metal as a surface finish onto the base metal, whatever that may be. And in a moment, I'll show you what I showed you last week, and that is that electroplating is used to put tin onto steel to make tin plate. You might say, why would you want to do this apart from corrosion protection? Well, the other main reason is to give a bright, shiny finish to the object, to make it look good, to give it a decorative finish. And also to add that having a shiny finish also means you've probably got better corrosion protection than you would have with a rough surface. So those are the main reasons we do it. And it's done on a huge scale commercially. And the basic idea is that you put your object and you normally hang it from some kind of hook, as you can see here, in a liquid. And you have another electrode, which is permanently inside the liquid. And you put a power supply between the two electrodes. You have one electrode here, which is the counter electrode. And over here, you have the working electrode, which is the object being plated onto. And the liquid electrolyte contains ions. And the basic idea is we put electric current through and we deposit on the cathode the metal that we're interested in. So it might be zinc, for example, it might be tin, and so on. And normally the counter electrode is made of the same metal that we want to plate. So for example, if we were plating tin onto steel, let's say this is a piece of steel and you're putting tin onto it, then the counter electrode would also be made of tin. And the liquid, what we call the electrolyte or the bath, also contains tin in solution in the form of ions. And in order to make sure that the solution strength remains constant, then we have an electrode made of the same metal of tin. And the idea is that as we deposit tin from the solution, we replace it with fresh tin from the electrode. So the counter electrode slowly dissolves and gets smaller, whilst we build up the thin but finite layer onto the object. And if we do it right, we can plate many hundreds, even thousands of objects with just one electrode. So this stays in the bath continuously, and these just stay in just once, get coated, and then get taken out and replaced by another batch. And this process just goes on and on, many hours a day. So another area where we use often electroplating is in the jewelry industry. So if you have a nice piece of jewelry, you may find it's been electroplated, and you can plate it with almost anything. Typically, you would use platinum and gold as the material that's actually being electroplated. And this might be on a base metal made of brass, for example, or bronze or something, maybe even steel for that matter. And silver is another one. Silver electroplating is very commonly used. So the electrochemical process should be fairly straightforward. And I'll give you an example of what we might do in the laboratory later on. But the idea, if you look at this one here, is we have, this one's got copper sulfate as the electrolyte. And here we have a silver cathode, and we have copper sulfate. So what we're doing here is you're plating copper onto silver in this particular case. So we have a battery. It could be a power supply, of course, but in this case, it happens to be a battery, which is a negative terminal going to the cathode and the positive terminal going to the anode. And we have what it says here, oxidation. If you can read it, it's rather small letters, I apologize. Oxidation takes place on the anode and reduction takes place on the cathode. And if you look at the diagram underneath, this is a generic diagram, it could be for anything. So we have metal A and metal B in this case. And here's the negative electrode, and here is the positive electrode. So metal B is the anode, And what it's doing, it's slowly dissolving. You see it's coming off here and getting smaller, just like I mentioned a moment ago for the tin plating bath. And then that moves through the electrolyte and it gets deposited on the cathode, where we get electroreduction happening. So we always deposit the metal we're plating onto the cathode. So the object we want to plate is always going to be the cathode. It's always going to be the negative terminal. And the material, which is the supply of material, if you like, the reservoir of metal, let's say silver in this case, is the anode. And it made out literally solid. It would be 100% metal. So if this was silver plating, that would be 100% pure silver. And it will probably last, say, a month or several weeks before you have to replace it. In other words, when there's nothing left in the solution. And that might coat thousands and thousands of objects with a very thin layer of silver. So this is the basic idea behind electroplating. Here's another diagram showing exactly the same thing. What this is showing actually is the electrons. These little red blobs are the electrons coming off and going into the power supply and coming back out again. So these little red blobs here, these little red circles, are the electrons. And they come and they fill the hole left in the ion. This little cutout here was like a mouth bite, represents where the electron's going to go into the outer orbital of the metal. One of the outer orbitals of the metal, I should say. And so therefore we reduce the metal ion. So this is an ion in solution, and this is the same ion with the now acquired electron forming the metal in its zero oxidation state. In other words, the pure metal deposited all over the surface. And if we do it properly, then we'll aim to get a thin layer, probably, let's say 10 microns or 50 microns. It won't be much more than that. About say 10 microns is a fairly typical thickness for an electroplated layer. Like I said, it's an industrial process, so it's done on a very large scale. So in reality, an electroplating plant is going to look something like this, with a gantry where somebody can walk up, and these are the baths here, and there'll be some kind of crane. Here's the crane, probably moves backwards and forwards, lowering the objects in automatically. So this is as automated as possible. And there are many thousands of different plants all over the world doing this for different types of electroplating. This is my lab experiment, which I'm hoping to make a video for. Normally you do it yourself, but as of the moment, we're not able to do it yourself, so I'm going to do it for you. So I'll try and make a video for this. And just to show you what's happening here, and by the way, this is an extract from an examination paper, which I have set in the past and probably will set again. And this is actually my model answer, as if I was doing the examination myself. So that's why it's hand drawn. So just go through this a little bit. What we're doing here is we're plating zinc onto copper. So here's our copper electrode, which is the negative electrode, like I just said. And here's the zinc, which is going to dissolve. So this is like a sacrificial anode, if you like. In fact, indeed it is, because it's going to dissolve. And this round circle with a V in it represents my power supply. And in the question, I specified that it runs at 4 volts and it delivers 1 ampere of current. And here's the tank, which is shown in cross section. So it's just like a glass beaker. And inside here, we have the electrolyte, which is made of zinc sulfate, otherwise shown here. And what happens when you put the current on, the copper becomes negative and the zinc is positive. So therefore, the electrons are going to go in this direction. So the electrons will start here in the zinc metal, and they will form zinc 2+ ions, which go into the solution like this. And the 2 electrons that are missing here, they go into the metal and they come out of the wire. They go through the power supply and back out into the copper. Therefore, it's negative, and therefore it's a cathode. And then we have the reaction of zinc being plated out. And this is the reaction of the plating process itself, shown here. We have zinc ions, and they pick up 2 electrons, and they form metallic zinc or zinc metal on the surface of the copper. And depending on how long we run this for, we can build this up to any thickness we want and just continually grow. Typically, we might go till it's 10 or 20 microns. We probably wouldn't want to go much thicker than that in practice, but enough to give a clean, clear coating. And the reason why I chose zinc and copper is because when you do this experiment, it's very obvious where you've plated it because the color changes. So the copper is going to be a dull red color, and the zinc's going to be white in color, or slightly gray, in fact. So therefore, it'll be obvious when you do the experiment, the color change. So that's why I've done it this way. And also, zinc plating is fairly easy to show in the lab. You don't need anything more than zinc sulfate to do this. You don't need any other chemicals in here, like some baths have. So the overall reaction then in this case is we have zinc sulfate. Zinc sulfate is made of Zn2 plus ions and SO4 2 minus ions. So the sulfate ion here, SO4 2 minus, would be the same if you had sulfuric acid, but in this case it's zinc sulfate. The sulfate doesn't do anything. So the zinc sulfate solution concentration remains constant. It's important to understand that in this process, the only thing that's actually happening, the zinc is dissolving to form Zn2 plus, is traveling across the gap to where the copper is, and the reverse reaction's happening here, where the zinc ions are picking up the same 2 electrons they had a few seconds earlier and forming metallic zinc. So the whole turnaround process is just simply transferring metallic zinc from one side to the other via the intermediacy of this electron transfer process, which is why it is an electrochemical process. So this has all the features of electroplating in one simple operation, which you could easily understand. And that's why I set it as an exam question, in fact, because it is fairly straightforward. And moving on, let's look at some of the underlying principles you need to know to actually calculate how much material we've actually deposited. So this diagram here is very important. It's important to understand the principle. What's happening is, first of all, the charge has the symbol Q. And this is given by the current multiplied by the time, IT. Current times time is charge. So if you remember back to your days of electricity, you'll know the electric current is measured in amperes. And the basic unit for an ampere is 1 coulomb per second. So 1 ampere is exactly 1 coulomb of charge being transmitted or transferred in 1 second. So if you want to know the total amount of electricity passed through this process, let's say we run this for 1 minute, that will be 60 seconds. And let's say it was 1 amp, then over a 60-second period, we would have 60 coulombs, because it's 1 amp is 1 coulomb per second. And if you use this equation here, Q equals I times T, and T is in second, and if that's 60 seconds, and I is 1 amp, then Q is going to be 60 coulombs. So I hope you get the idea that when we determine how much metal is being put down on here, we're actually going to use Faraday's laws. And Faraday's law tells us how much metal is deposited for every single coulomb of charge we pass from the power supply. So in other words, in order to calculate how much material you're putting down, you need to know 2 things. 1 is the current in amperes, and 2 is the time. And rather surprisingly, you don't need to know the voltage for this calculation. Although this represents the amount of energy, in Faraday's calculation, in order to work out how much we deposited, we only need to know how many coulombs of charge we've actually passed. And we also need to know how many electrons there are per ion or per atom of metal. So in this case, the number of electrons is 2. So it's very important to know this number, and it's very important to know this number as well, and the time, but you don't need to know this number. So when you look at the equation here, if you want to know how much metal is actually being put down in grams, then you need to use this equation here. So in little case in red, we have the lowercase m representing the mass of metal in grams is equal to the atomic weight of the metal, capital M, multiplied by the charge passed, which we calculated just here, divided by the number of electrons in the charge transfer process, and then multiplied by the Faraday constant. So I've written it down here. M is the atomic weight of the metal. That's this one here, the blue one. In light blue, well, actually brown, no, it's gray, I should say, in gray, lowercase n is the number of electrons in the reaction. If I go back to this diagram here, N in this case, where I'm putting the cursor now, is 2, because we need 2 electrons to electrolyze one zinc ion to make 1 atom of zinc metal. So N, lowercase n, N is 2 here, and that 2 is this value here, and it goes in here. So just to recap then, if you want to calculate the mass in grams, we need to know the molecular weight or the atomic weight of the metal concerned. And then we multiply by the charge pass, which we measure. We divide by the number of electrons in the charge transfer process, and we divide again by the Faraday constant. Now, the Faraday constant here is shown in pink, has a value of 96485 coulombs per mole. And what does that mean? That means that if I was to go back to here and I was to deposit 1 mole of this metal, then that would take 96,500 coulombs multiplied by 2, because I need 2 Faradays worth of electrons per ion. So to make 1 mole of zinc metal, I need the Faraday constant multiplied by 2 number of coulombs. And that's shown here. If I show it here, for example, so F is 96485 coulombs per mole. This is a universal constant. It always has this value. You can round it up to 96,500 if you want to. And in the old days, when I was in high school, that's what we did. But if you want to be more precise, this is the exact figure. Then you need to know this reaction here. Since we're talking about electrodepositing zinc, we need to know that the reaction is zinc 2 plus 2 electrons forming zinc metal. You need to know this, otherwise you can't calculate anything. And then the only thing that's missing now is what is the atomic weight or the molecular weight of zinc. And it's this value here, it's 65.38. And if you remember your chemistry, you'll know for a metal, the atomic weight is usually expressed in grams, actually, or gram atoms. So put that slightly differently, 1 gram of zinc has a weight of 65.38 grams. Sorry, that's a mistake, I'm sorry to say. 1 mole of zinc, or 1 gram atom. Yeah, I'll rephrase what I'm saying, because I'm confusing you. A gram atom is the same thing as a mole. 1 gram atom, in other words, 1 mole of zinc, has a weight of 65.38 grams. So let's do the calculation then as if it were in an exam question. So the question says, use the Faraday equation to calculate the weight of zinc electrodeposited on a copper sheet. And here's our now famous formula, which hopefully you will know. But if you don't, then M is the mass of metal in grams. Q is the number of electrons in the charge transfer step, which is 2 in this case. F is the Faraday constant, 96485 coulombs per mole. M, uppercase M, is the atomic weight of the metal, which in the case of zinc is 65.38. So the Faraday equation says that the charge pass is the current multiplied by the time. So the current in this case is 4 amps, and the electrolysis time is this. It's 5 times 3,600 seconds. 3,600 is the number of seconds in 1 hour, 60 times 60. And this is for 5 hours. So this is a 5-hour test. And then the reaction is zinc 2 plus 2 electrons going to form zinc metal, where N equals 2, number of electrons per electron transfer. So the weight then is 65.38 multiplied by 4, multiplied by 5, multiplied by 3,600, divided by 2, multiplied by 96485, and it comes out at 24.39 grams of zinc electrodeposited. So that's the exact answer to the question.